Every object with mass exerts a physical pull on every other object. That includes everyday items, right down to the objects sitting on your desk. You don't see things sliding toward each other because that mutual pull is incredibly weak. It is completely overwhelmed by the friction of the surfaces they rest on and the massive downward anchor of Earth's gravity. Isaac Newton formalized this reality with his universal law of gravitation, an equation proving that any two masses in the universe pull on one another. There was a glaring limitation for scientists in Newton's era. Looking at this equation, you can measure the masses, the distance, and the resulting force. But the formula is incomplete without the exact numerical value of the gravitational constant, or g. Finding g presented a unique measurement conflict. To calculate the constant, you have to measure the gravitational force between two small objects. But you can't measure that tiny force without the background gravity of the Earth drowning out the signal. In 1798, an English scientist named Henry Cavendish attempted to solve this problem. To find the numerical bridge between the gravity we feel and the gravity of the stars, Cavendish had to figure out how to isolate the weakest force in nature from the mechanical noise of the entire planet. Cavendish realized that trying to measure gravity by pulling objects together in a straight line was a dead end. Even a slight amount of surface friction would ruin the data. His solution was a highly sensitive apparatus called a torsion balance, designed to sidestep friction by suspending the experiment in the air. Suspend a lightweight bar of length L from a single wire with two small masses at the ends. Place two massive lead spheres on opposite sides. Their offset gravitational pull creates a twist, a rotational force called torque. Because the whole assembly is hanging, there is zero surface friction holding the masses in place. By turning a linear tug-of-war into a delicate horizontal spin, Cavendish successfully isolated gravity on a miniature scale. The suspended bar doesn't spin forever. It is eventually stopped by the physical limits of the wire holding it up. As the wire twists, it generates restoring torque. This is the natural mechanical resistance of the wire fighting to unwind to its starting position. This resistance depends on the wire's stiffness and the twist angle, represented by theta. Eventually, the bar reaches equilibrium, where the sphere's gravitational pull perfectly matches the wire's twist resistance. This balance creates an algebraic equation equating gravity to physical tension. The engineering of the torsion balance leaves g as the only unknown variable. Everything else in the equation can be weighed, measured, or calculated. In his laboratory, Cavendish recorded the tiny angle of rotation before the bar came to rest. By solving the equation, he revealed the value of the gravitational constant, 6.67 times 10 to the negative 11th power. Expanding this exponent into full decimal form shows a microscopic number, explaining why everyday objects don't visibly pull each other across a room. With g finally known, scientists could plug it back into Newton's equations to solve mysteries far larger than lead spheres on a table. Because the radius of the Earth and the acceleration of falling objects were already known, scientists used the constant to calculate the exact mass of our planet for the first time. Because this constant applies everywhere, we could observe the orbital behaviors of distant planets and finally determine the mass of the Moon. Through the microscopic twist of a wire in a quiet 18th century laboratory, Cavendish provided the specific value required to weigh the entire cosmos.